Theorem 32 is probably, as I mentioned in this sentence right here, probably the most important theorem of the first half of the course. It's one of the reasons that we're ultimately going to care about projection. And what it says is that if I have an orthonormal basis for my entire vector space, if my entire vector space is Rn, let's say, if I have an orthonormal basis for Rn, then we can recover any element of Rn at all, any vector x, is equal to the sum of its projections onto each of the vectors in that basis. This is something that need not happen if your basis is not orthonormal, but if your basis is orthonormal, then x, any vector, is equal to the sum of its projections onto all of the VI's. That's significant in a way that is hard to really appreciate in the finite dimensional situation as we have here, but this is going to be the most important fact we're going to need to infinite dimensionalize in order to unlock the second half of the course. So this is a pretty fundamental result, and I'd like for your team to take a crack at proving it. The hint is that lemma number 26, if you fill in lemma number 26 appropriately, you can use it to prove theorem number 32. But I think I realized as I was browsing around the room that what you need to prove theorem 32 might not be just lemma 26, but it might actually be another result. That's not from this sheet, but actually was a result from homework number 1. And so the result I'm thinking of is the following, and maybe this will change your thinking about how to prove this theorem. I don't remember which problem number this was, but the result said that if P is a projection matrix, and if that projection matrix is invertible, so most times when we make a projection matrix, we don't get a matrix which has an inverse, because the rank of a projection matrix is equal to the dimension of the subspace onto which we're projecting. But if we have a projection matrix which is invertible, then who remembers the conclusion of this theorem? What does P have to be if it's an invertible projection matrix? The identity matrix. P must be the identity matrix. So I think this might be the key to proving this theorem. Because what we need to do to prove this theorem is to establish, first of all, what's going on this right-hand side of the equation. If you factor out the x on the right-hand side of this equation, then what matrix is x being multiplied by, really? Plus Vn transpose. This is really the same thing on the right-hand side as what we would get by taking a matrix whose columns are V1 up through Vn, multiplied by the transpose of that same matrix, V1 up through Vn times x. So in other words, what we have on the right-hand side of this equation is A transpose times x, if A is the matrix whose columns are our vectors V1 up through Vn. So that's one way to see what's on the right-hand side. The question is, why should that be equal to x itself? Well, what do you see that's up here on the screen that could make that connection? A times A transpose should be the identity matrix. Well, why should we expect A times A transpose to be the identity matrix? Okay, so there's a couple things going on here. First of all, why is A times A transpose a projection matrix? A times A transpose is a projection matrix because, say again? Why is projection as easy as AAT? What's true about the vectors V1 up through Vn? Under what circumstances is AAT as simple as our projection matrix? Well, that's our second step. We need to establish that second. But first, why do we get away with just AA transpose instead of A times the inverse of A transpose A times A transpose? Because they have unit length and are orthogonal, right. They have both properties. So because that's an orthonormal set, AA transpose is exactly the projection matrix onto the column space of A. So that's fact number one. And then fact number two, using this homework result, we need to know that therefore AA transpose is equal to the identity. Or I should say P is equal to the identity. That's probably a better way to say it. P is equal to the identity. And all we need to do to justify that is, how do we know that AA transpose is an invertible matrix? That's the last link in the chain here. And maybe I'll leave that one as a cliffhanger so that we can finish putting all these pieces together first thing on Monday. Because AA transpose is invertible. So if we can put those pieces together, then we get a proof of what's going to be probably the most important theorem in our course. That if we have an orthonormal set, then any element in its span can be recovered as the sum of its projections onto each one of those vectors. These two elements will provide the proof in a way that we'll see first thing on